Okay, here we are on page 4 of math induction. So first thing we're going to do is we are going to, I put my template here, and we start out, and do you see how lazy I am? I didn't want to rewrite this thing here, so I just positioned it so I'm showing that, hey, P subscript n, which is the proposition of the conjecture, is that 7 to the n minus 4 to the n minus 3 to the n is divisible by 12 for all n that are positive integers. So basically that's saying n is 1, 2, etc. Right? Okay. So first we're going to do the base case, which is we're going to take the first index, which is 1. So if n equals 1, what happens? So if n equals 1, then this expression here is going to be 7 to the 1 minus 4 to the 1 minus 3 to the 1. So that's equal to 7 minus 4 minus 3, which is 0. Is 0 divisible by 12? Yes. So equals 0, and 0 is divisible by 12. So therefore, P of 1 is true. Now, we're going to go to the step case. So we take first P of k, and the way we get P of k is we simply make n equals k in the original expression. So we'll say 7 to the k minus 4 to the k minus 3 to the k. So if that is true, then this expression is divisible by 12. And the way we show it's divisible by 12 is we say, oh, it's equal to 12a, where a is an integer. Okay, so we're assuming this to be true. We don't know that it's true. Okay, now what we're going to do is we're going to write about P of k plus 1. So how are we going to do that? We're going to take the original expression and we're going to put k plus 1 in for n. So 7 of k plus 1 minus 4 of k plus 1 minus 3 of k plus 1. What's that equal to? Well, what we're going to try to do, remember, is we're going to try to algebraically manipulate this until we get something that looks like this, and then we could substitute in like 12a, right? So let's try to do that. So 7 of k plus 1 is equal to 7 times 7 of k. Do you see how we're trying to make it look like that? 4 to the k plus 1 is equal to 4 times 4 to the k. 3 to the k plus 1 is equal to 3 times 3 to the k. All right. Now, if we try to, let's see, substitute in for 7 of k, what if we tried to substitute in something based on this? So 7 of k is equal to 12a plus 4 to the k plus 3 to the k, right? What if I substitute in for 7 of k, what if I substitute that expression in? So let's see what happens. So 7 times 12a plus 4 to the k minus 3 to the k minus 4 to the k, 4 times 4 to the k minus 3 times 3 to the k. Okay, and then now let's, oh wait, this is plus here, right? Plus. Okay. So now we have 7 times 12a plus 7 times 4 to the k. And we have 7 times 3 to the k. And then we have minus 4 times 4 to the k. And we have minus 3 times 3 to the k. Now I'm seeing some common, I don't know what you call it, common terms, they look alike, don't they? They're like terms. Sorry about that. So I'm going to add the underlined yellow like terms. So 7 minus 4 would be 3 times 4 to the k. Now I'm going to do the yellow box terms. 7 minus 3 is 4 to the 3k. And that's times this, okay? And now what I'm going to do is I'm going to factor out a 12 from each thing. So I could do that by, I would have 7 times 12 12 times 7a plus, and if I factor out a 4 here, I would have 4 to the k plus 1, a k minus 1, right? And here I would have 4 times 3 to the k minus 1, right? Okay. Now I have a 12 there and a 12 there also. I can factor out a 12 from everything. Then I'll have 12, 7a plus 12, and I factored that out, 4 to the k plus k minus 1, plus 3 to the k minus 1. So all I need to do now is figure out if this yellow part here is an integer. If it is, then I have proven that it's divisible by 12. Well, we know that a is an integer, so 7a is an integer. What about 4 to the k minus 1? Well, if it was 4 to the k, for sure that would be an integer because k is an integer, a positive integer. What about k minus 1? Well, the smallest value that k minus 1 could be would be 0, right? Because k could be as small as 1 because the smallest value here is 1, okay? But it's not going to be any smaller than that. So 4 to the 0 is 1, so we know that this is an integer, the smallest value could be 1, and this is also an integer, smallest value could be 1. So we know that 12 is times an integer. So that means that the expression that we started with, which is that, we're going to put it here, 7 of k plus 1 minus 4 of k plus 1 minus 3 of k plus 1 is divisible by 12. If 7 of k minus 4 of k minus 3 of k is divisible by 12. And so we've proven it, and all we need to do now is specify the n value, and we know that n is a positive integer because it starts at 1 and goes to infinity. That's it. Okay, now we're moving on to the next one, which is from section 9b2, number 1, part A. Use the principle of math induction to prove that the following propositions are true for all positive integers n. So this first one is a summation of all numbers from 1 through n, and we're saying that that is equal to n times n plus 1 divided by 2. This is something we're familiar with from arithmetic sequences and series, also from just probably previously in your math life, you added up all the numbers from 1 to 100 or whatever, and you have a formula for that too. It's true when n is greater than or equal to 1. Okay, so let's look at the first case, or the base case, which is when n equals 1, what happens? When n equals 1, I'm going to rewrite the summation. It's just going to be I equals 1 to 1, so there is no summation actually. It just says 1 is equal to 1 times 1 plus 1, which is 2, divided by 2, which is equal to 1. So 1 is equal to 1, and that's true. So therefore, P subscript 1 is true. Now we go to the step case. So the step case says, let's assume that P of k is true. And if P of k is true, then what do we know? So let's take the expression that has n's in it and just put k's in it. So basically we say if P of I equals 1 through k, we know that that is equal to k times k plus 1 divided by 2. And so that's what we know if P of k is true. Now, remember, this is a proposition, so we don't know it's true for sure, but in the step case here, the first thing we do is we assume that the kth case is true. Now, what we're going to do now is we're going to take the k plus 1th case, and we're going to write it out. So it's I equals 1 to the k plus 1. And we want to try to manipulate it algebraically so that we can do this substitution on it. So let's see, if I have I equals 1 to k plus 1, the summation of 1 to k plus 1 of I can make it look like this part of it by separating out the I equals 1 to the k part and add separately the k plus 1 term. And if I do that, then I know that this part is equal to k times k plus 1, because we assume that to be true, divided by 2. And then I add k plus 1. Now I know, I can combine these two terms into one expression by putting a common denominator on it. So that would be 2 plus k times k plus 1 divided by, do you see what I did? I factored out the k plus 1 from each of these. And the bottom is going to be 2. I'm going to do that in 2 steps. Okay, so first what I'm going to do is I'm going to put everything over 2. And I'll have k plus 1, plus 2, k plus 1. And now what I'm going to do is I'm going to factor out k plus 1 from both. So I'll have k plus 1 factored out, and it'll be k plus 2 left over. And now I've actually proven it, because if you look at it, I got this. Oops, not this. I got this, which is my left side expression. And look at this one. Do you see how if my n value is k plus 1, this would be n, and this would be n plus 1. So I have shown that this is true. Okay, so I can say down here, thus, sigma of I equals 1 to k plus 1 is equal to k plus 1, k plus 2 divided by 2 if, and then we put the p of k expression here. The summation from 1 to k is equal to k times k plus 1 divided by 2. So, since p of 1 is true, and p of k plus 1 is true whenever p of k is true, then p of n is true for n is greater than or equal to 1. Okay, that's it for this page.